Hello community! Today we do physics with multiple AI agents. Now imagine this is your address, MIT, Cambridge, USA, Laboratory for Atomistic and Molecular Mechanics. And you have a simple job. Hey, just code some physics-aware, multimodal, multi-agent AI system to help us discover some new alloy designs for spaceships. Plus, your tools that you can use. You can have a multi-agent system, multiple LLMs, multiple vision language models. You have access to all the atomistic simulation Python programs here at MIT. You can do scientific machine learning, multimodal generative AI systems, and you have access to the complete database and the library of all material science in the world. So, let's do this. And this is what we will come up in about 10 minutes time. So we have a user input, and then we have multiple agents. We have a network of agents. And each agent has a particular task to do. And we will have here a planning tool with an LLM that will develop for our particular task here a task description and a task process schedule that we will do. And then, for example, we can have a critique LLM that makes sure that this planning tool really has some good plan, and then we just jump to the computation. And if we know exactly what we have to compute, for example, the lattice constant, or some dislocation configuration, or some, in general, crystalline constant, we want to find out how to find here the optimum energy density. How often you want to do this, for example, 20 times. This is all done here by our multi-agent network without any human influence. And then if you have a coding tool and you have a plot analyze tool and all the mathematical simulation comes back, and then we have here from our plot analyze tool, we have now the final results from all our agent, and we see here, for example, a particular energy change standard deviation. And then we say, okay, now activate another discussion agent, let's say a physics professor. And let's have a discussion with this AI system as a physics professor. And let's have a look, what can we learn from this and how can we optimize it? Do we have some ideas? Do we have some hypotheses? How can we validate our new hypothesis? How can we learn faster? So just to give you a short visualization, this is our multimodal data. So what we have all the computer programs from MIT for material science. Then we have access to all the material databases on the internet. Then we have access to all the different models, LLM, VLMs, whatever you want. Then, of course, you are here studying material science at MIT, so you have a complete theoretical understanding of theoretical physics and mathematics. Then we have access here, let's say via RAG, to all the papers, all the books that are in the library, and we can do experiments. And we have visual data from our experiments, so we can see what is happening in our experiments and maybe then cross-check it with computations. And if you understand this here also from my latest video, and as you can see, I try to build up a little mini-series. So do you see here for the computation here we have for AI agents or agentless for software development, or here if you extract here from papers or books or PDF files, how and what LLMs or what polysystems you can use. Or if you have here the AI models and you want to have a knowledge graph established, how to build your graph RAG, or you go with a speculative RAG or whatever system you want to use. So you see, I'm trying to build up my little mini-series. But what we have is a network of AI agents. We have multimodal data. We have atomistic simulation, computer simulation, and we want that our AI agent put it all together for have a faster research phase. And here's the publication we're going to talk about, mid of July 2024, AtomAgents, Alloy Design and Discovery through Physics-Aware, Multimodal, Multi-Agent, AI. Beautiful. MIT. Great. So, at first, understand we have multiple agents. We will have here with the role of a user, with the role of an engineer, with the role of a scientist, with the role of a group manager who coordinates all those agents. And each agent is, of course, here powered by a very powerful LLM or a vision language model from the GPT family from OpenAI. Then we will integrate here access to all our physics, to all our mathematical simulation Python programs with this AI, so AI can really test out this run simulation autonomously and try to understand what is the result of this mathematical simulation. For example, here, enhance the design process of crystalline materials at an atomic level. And then we have, as a network of agents, we hope that those agents are intelligent enough to integrate now diverse data type. You have seen everything from textual information and scientific literature to visual data like plots and simulation images. When we want to enhance now the data analysis and the predictive capabilities of our complete AI system. Isn't that beautiful? As I told you, we want to have this as an autonomous operation, only steered here by the most intelligent LLMs and VLMs on this planet. We want to have an interpretability and an accessibility, so we understand what decisions were made by the agent. It is all traceable, and we can have, if we want, a human oversight. And you immediately understand this is not just here for the development of alloys. You can have this also for biomedical engineering, for renewable energy, from anything that is about environmental sustainability, anything about new materials and optimization processes. So let's build our network of agents. And in the most simple case, and we have here 4 different tasks here that MIT performed. Let's say we have an agent role that is a user. This is the human user who says here, this is my task. And this is exactly what then the AI system should solve for us. So then we have an assistant. This is, for example, here GPT-4 Omni. And the task of the assistant is to execute a plan developed by the planning tool. And then we need here the best, GPT-4 Turbo, for really complex argumentation. The role is here as a scientist. The leading material scientists have been fine-tuned on all the material publication of the last 10 years, all archived preprints on material science, mathematical simulation, mathematical computation, whatever. Then we have a group chat manager. So this one manages what LLM is allowed to participate in how the communication is structured. Planner, this is really important, so we make here GPT-4 Turbo again our main workhorse. So we have to come up with a plan to solve here the user problem. The plan should include the function and the required input parameters for each and every agent that will take care about his particular part. And the plan should be approved by the critic, and then again we have another GPT-4 Turbo LLM just for criticizing, just for checking, hey, double check the plan from the planner for the completeness and the correctness that we are really able to do our task as defined by the user. Now, how to implement this? MIT tells us, hey, we use here the AutoGen framework. If you're not familiar, October 2023, AutoGen enabling next-gen LLM applications via multi-agent conversation. Pennsylvania State University and Microsoft Research. I recommend this particular preprint for you if you want to have a little bit of a deep dive, because they explain really nice step-by-step how to use here the AutoGen to program here a multi-agent conversation. And you have here also the code, so you see whatever you want that your particular agent that has been the LLM, I don't know, pre-trained on the last 10 years of material science A publications, that exactly where does it integrate, how does it integrate, real nice flow description here. Beautiful. And then we come back to MIT and they say, okay, how we design now the agent. And they say, okay, all our agents here use here the GPT-4 family models. We have here the implementation in the AutoGen framework I just showed you. This is an open source ecosystem for agent-based AI modeling. And then for each of their system now, they tell us, hey, for this we use here the proxy, user proxy agent class from AutoGen. And for the assistant and the reviewer agent, in the knowledge retrieval tool, we use here the retrieval assistant agent class. And for the plot analyzer, they use here the multi-modal conversible agent class. And beautiful. Now, and they tell us, hey, all data and all codes are available on GitHub. And this is here the address. Beautiful. Now, from the original MIT publication, we have this kind of visualization just to show you the complexity of tools that we have. So here, we start here with a planning tool. And in this tool here, we have multiple, if you want, LLMs. You have a planner, you have the critique LLM. Normally, both are GPT-4 Turbo, but different systems. Then we have here, for example, the coding tool. Then we have here the core tool where all the central coordination is done. Here we have the computation tool. Here we have the plot analyze tool. And here we have our knowledge retrieval tool with assistant and reviewer and everything. And of course, we have a little bit of memory for each agent. And then we have here at the crosslinks, we have here our core memory and our core functionality. Beautiful. So let's do this now. MIT gives us 4 experiments. I only tackle experiment number 3 and experiment number 4 because the other 2, they are just simple. You can read this if you want. But let's have a look here. Experiment number 3, multi-scale mechanics problem by calculating the critical fracture toughness of some specific alloys at varying concentration. And the experiment showcases here the system's ability to integrate the theory of material science, all the computer simulation, and finally the data visualization that could give us further insight into the experiment. And then experiment 4, this is not the most complicated, will explore the system's ability to generate and validate new hypotheses using here Pyle's potential, never mind. And this will demonstrate the AtomAgents' potential for driving scientific discovery. And is it able to be much faster than humans? If humans code and humans perform this thinking, can we really accelerate here the discovery process for new materials? So here we go. Experiment 3, multi-scale mechanics problem. And we have here the fracture toughness in alloy system. So the user has here specific task input. Beautiful. And then we have here particular agent in our configuration. You choose what agents you want to build. You choose what agent you want to integrate, how they communicate, what is their main topic, how they are coordinated, and. Here, for example, we have, again, core agents have a planning tool, a computation tool, another computation tool performs simulation, completes now the frankness calculation, the results of 2 and 3, adds them together. Then we plot here the complete result. And then we ask here to analyze the plot generated and discuss the result. So you see a lot of agents talk together, interact together. But let's say this was the task of a human, and this is now the result of our multi-AI agent system. And they compare now here for the system A and the system B, never mind what it is, here some particular behavior. Let's do the process at first. Here you have everything that goes through, beautiful. And then we have here our specific agent, our specific tool to analyze the plot. And our specific agent to analyze the plot has, of course, here the GPT-4 Omni, our visual model here. And as you can see, GPT-4 Omni writes now here what it understands, what GPT-4 Omni thinks is the result of this block. And this is quite detailed. This is quite to the point. Look at this yourself. This is really, you can do some research now. If you have your GPT-4 system trained on this, if you have additional RAG functionalities, if you bring in all the data. So this is now an interesting interplay of AI agents. So multi-agent empowered by GPT-4 captures here all the details of the plot, both quantitatively and qualitatively. This includes identifying the maximum and minimum values for some fracture toughness for the crack system and provide a detailed discussion on the variation of fracture toughness related here to some particular concentration. Never mind the physics, it is just about the interplay of AI agents. And then I showed you, and then we activate now an AI scientist. And then we want just to make sure, like you ask, and you ask a human colleague, you can now activate another LLM system, an AI scientist who has been especially pre-trained on material science. And then you say, hey, let's discuss this and this and this. I have this idea. What do you think about this? And then the scientist, and here, of course, we have GPT-4 Turbo again for the most complex analysis, says, look, this could be, or maybe this is, or this could be an implementation. So you see, we have here kind of a simulation of a human conversation of two experts on this system. So to facilitate the hypothesis generation, a scientist agent is now integrated in the model. Yes, integrate. You have multiple agents. You can have here just your research idea, or you build some knowledge graph now here that you say, give me the understanding in a knowledge graph. What new connectivities do we have between our nodes? If some of the characteristics are now nodes, what are now the new edges? At what temperatures do they establish themselves, and so on. Beautiful. Give you another one. This is now experiment number 4, hypothesis generation and validation. Now a little bit of a meta problem, but we will use exactly here the same agents. We have exactly here, and now this is our particular input. This is an hypothesis that there's a positive correlation between the Peierls barrier and the potential energy chain standard deviation due to some dislocation movement. And user goes on and says, hey, can you test this hypothesis by using now the atomic simulation on a particular system in the particular interval at a particular whatever. And then our multi-AI agent goes on and says, okay, I understand the task. I plan now how to do this. The action planning tool sweeps in. The plan is approved. The critique says, okay, let's go. Then we have the computation tool to activate to find all the Python programs that we need for this. Start it, run it, API call, whatever. Function calling, coding tool, analyze it. We have the result plotted. And then also we can have here, if you want here, a discussion with the AI system. Hey, what do you think about this plot? What does it show us? Can we have, is this now supporting our hypothesis, or is it here counter-arguing, and what can we find out about this particular alloy? So there's a lot of generation going on here with a multi-agent, multimodal thing. So what we have now is an autonomous, physics-aware, multimodal, multi-agent framework for accelerating here, in our particular case here, the alloy design and discovery through advanced computer simulation. This looks nice. We focus only here on the computer science, on the multi-agent interdependabilities, how to orchestrate here the interaction operation with this system. But MIT tells us, hey, listen, however complex you make your agent and you build your tools, there's one component that it is heavily depending, the complete performance depends on this. And this is the capabilities of each LLM or each vision language model that you use in your agent. If the accuracy and if the performance here of those LLMs is not top-notch, the whole chain can crumble down. So careful, the quality of each LLM that you use is important. So whatever you build on a complexity of multi-AI agent system, for each agent, each LLM that is working here in the background of the agent, you have to really choose the most capable LLM system for the task. And yeah, and then suddenly I found, because I went to GitHub and I wanted to see the code, and then they told me, hey, alternatively, the GitHub code will be provided by the corresponding author based on reasonable request. So I don't know if you go there whenever you see this video. Maybe if you go to GitHub, LAM, MIT, AtomAgents, then you see the code. Recording this video, this is not a public repo here on this particular address, and I will have to get in contact with the corresponding authors and ask here for a reasonable request if I can have a look at this. But I understand that those MIT programs and the simulation here of alloys are valuable to MIT, and of course, this is not an open source code. Great. So it left me now with one question, and we have to answer this. What is the performance of this system? Poor, average, good, maybe excellent? Who knows? So luckily I could find here just 2 days later, mid of July 2024, another beautiful preprint. And we have here Spider 2, now the visual extension, and they examined here Google Cloud AI research and Google DeepMind and Salesforce research and the University of Hong Kong and Yale University. How far are multimodal agents, what we just looked at, from automating data science and engineering workflows? How good are they? Do we have benchmark data on them? And can we test them for their performance? And this is exactly what we need. And here in blue, it's so beautiful. Just 2 days later, they say, hey, data science and data engineering workflows often span multiple stages, from warehousing the data to orchestration using tools like BigQuery, dbt, or Airbyte. As vision language model advance in multimodal understanding and code generation, VLM-based agent could potentially automate these workflows by generating SQL queries, Python code, and GUI operation. And this automation can improve the productivity of experts and democratize access to large-scale data analysis. So yes, beautiful. So let's have a look at this. Our task here is, and we focus here on one particular dimension of this study, to evaluate the multimodal AI agents in a professional data science and data engineering scheme. So novel is the integration of code generation, like I showed you here with the MIT programs for material science, and the GUI control access for the complete data workflows for a real-world professional environment simulation. And they start very easy. Look at this. They say, hey, we start with a task 1. Load the data under the current Google Drive folder into a new table of the opened BigQuery dataset. And they take screenshot what you have to do this. Task 2. Save the top 20 dramatic movies from 2000 from the Snowflake database into now a new CSV file on your desktop. Where you have to go, what you have to click here, which marks exactly, screenshot, and so on. And they have hundreds of those tasks, from data warehousing, data ingestion, data transformation, data visualization, and data orchestration. So, a complete different set of tasks, but also multi-AI agent systems. And as you can see here, we have one real more complex. You collect, for example, your tutorials, you learn the tutorials, you write the instruction, you write the environment setup function, you write the task-specific evaluation function, and you cross-evaluate this on a virtual machine. Beautiful process. All of this was done. And here now the summary. If you want to have a detailed look at this preprint, here we have table 6, summary of all applications in Spider 2 Visual. And here we have different categories: the data warehousing, the data ingestion and integration, the data transformation, the data analysis and the data visualization, the data orchestration, traditional data processing, IT service management, and daily applications. And you see here again the data categories here with their particular application, and they are distributed quite nicely. Great. Now, I was interested, what is the complexity level? And here's just one line for you. So if we look here at the different levels, you see here, for an easy level, it's about 20%. The medium level is about 63%. And the real hard to solve complex level is just 17.4%. So it is not the most complicated benchmark to fulfill, but just that we have an idea. We're working here with a medium complexity in our benchmark data. Here's the overview of SPIDE2 visual given by the authors, the data warehousing, the data ingestion, the data transformation, the data analysis and visualization, data orchestration, the full data pipeline, the observation space, the interfaces, the professional tools that there were done. So let me come to the summary. We have a new multimodal agent benchmark for professional data science and engineering. And they have expert curated tasks, 494 tasks, and some specific task-specific metrics. And they now go here, as I showed you, a tree-modal fusion. You have visual screenshots, you have structured accessibility trees, you have natural language instructions, you have some rich content. Then you have some internet-connected environments. You have industrial-graded tools, BigQuery, snowflakes, realistic topics. You have to authenticate your API calls. You have a real diversity of your task, whatever it is, and you get an immediate feedback, and the whole thing is open source. And yes, this exists here. Go to SPIDE2, the new visual extension, GitHub.io, and you have here all the data and all the tests. This is really nice. Now, this is an overkill. We don't need 500 curated tasks, but we want to see what is the overall performance. How good is this network of AI agents? What is the performance data? And before we jump to the performance data, I just want to give you here the overall system prompt. Here on the left side, you tell the system, your LLM, hey, you are an intelligent agent who is an expert in completing data science or engineering tasks using professional tools on your computer. You have a deep understanding of computer basics and data science and engineering knowledge, and now you will interact with a real desktop environment, which is, here, Ubuntu operating system with access to the internet. You should strictly follow the user instruction, communicate with the environment, and try your best to complete the given data-related task successfully. In each iteration, you should take one action to control the keyboard and mouse. Yes, yes, yes. And then, besides, here are the important tips, and I had to laugh when I read this. Okay, you have your password, you have the screen size and so ever, and then they say, hey, do not be stubborn to complete the task in one step. You can break down the task into several steps and complete them one by one. Do not be stupid. So this is a human typing here the overall system prompt to an LLM. Do not be stupid to repeat the same actions without any progress. So real nice. And here on the right side, then you have the task-specific prompt. And yeah, you can go through this and you get a good idea what they tested. A real huge test field. And the results are this. These are the performance data. And let's just look here from our LLMs or our VLMs here at Claude 3 Opus, Gemini Pro 1.5, GPT-4 Omni, and GPT-4 Vision. And as you can see, for all the different tasks, if we look at the overall, the performance, the success rate of the best system is 14%. And for our Mixtral system and our Llama 3.7b and our Q1, the overall performance is sometimes below 1% or at 2% success rate. So you see the complexity of those tasks, and those are easy tasks, as you have seen, is not performing well. So this brings us back to reality. So whatever you build on a complex AI agent, on a network of agents, you have to expect, in the best case, a success rate of 14%. Great. Short summary, Spider 2 Visual, first data science and engineering benchmark, integrates enterprise professional application and support intensive GUI operation. Besides code writing across a full data pipeline, it contains 494 tasks, involves 20 professional tools, and provides a real-time executable computer environment. And the most advanced VLM, vision language model, our GPT-4 Vision, still performs poorly on this Spider 2 Vision, achieving a 14% success rate. So, yes, of course, if you want to see here more, this is here from github.com. The address, it is Apache 2 license. If you want to see the documents, if you want to see the code, if you want to see all the task example, go there, pick up your task that you are maybe interested in. There's some really interesting task description over there that I for sure will use for my work, and it is Apache 2 license. So great. And you know, just for curiosity at the end of this video, 2 months ago I did this video where I showed you autonomous AI agent, and there was a study that 2 months ago, their maximum performance rate was 14%. So it is a complete different complexity level on this video here 2 months ago, but the 14% barrier seems to be a real benchmark, no? Because now, even today, just 2 days ago, the most advanced VLMs also just achieve 14% success rate. So this gives us a good grounding. This gives us here an idea what we have to expect if we work here in a professional environment, in a commercial environment. This is the success rate you will expect and you will achieve. So I think we all see that we still have quite a long way to go to make those multi-AI systems reliable, transparent, that we can evaluate them, we understand step by step what is happening, and maybe one time we will reach a performance that is more than just 14%. I hope you enjoyed this video, I hope you found some nice idea, and it would be great to see you in my next video.